In the last section, we talked about the polarity of a bond. That's not necessarily the same thing as the polarity of an entire molecule. Let's look at that. Starting up with carbon dioxide, our old friend here. Let's analyze this molecule one side at a time. Let's look at this carbon-oxygen bond. We understand that the oxygen has a greater electronegativity, pulling power, than does the carbon. And so we would expect that the electrons would tend to spend more time towards the oxygen than over on the carbon side. And we might expect there would be a dipole there. Here are the electronegativities. What about the other side of the carbon-oxygen? Here, let's see. We've got, it's the same situation. We've got the oxygen with a greater electronegativity, and so we would expect the electrons to be pulled more over towards the carbon. But when you have carbon dioxide, you don't have one or the other. You have both going on at the same time, like this. What happens here? Check this out. The oxygen on this side is pulling the bonding electrons, but its effective nuclear charge can actually work towards the other side as well. And it can pull these electrons back in this direction. Likewise, you're over here. This oxygen can pull those electrons back towards the carbon. You've got two forces, one pulling that way, the other pulling the opposite way. Those two forces balance each other out. And as a result, there is an even sharing of electrons in the carbon dioxide molecule. It doesn't go like this. It goes like that. No? Yes. And so we find carbon dioxide is a nonpolar molecule. There is an even distribution of electrons in that molecule. Why? Because you have strong electronegativities on opposite sides and they pull in opposite directions, but that balances the molecule out. The electrons end up being evenly distributed. Let's look at boron trifluoride. We know fluorine has a greater electronegativity than boron because we can get that from the periodic table. And so we might expect that the fluorine would be more negative than the boron. But consider this analogy. You've got three people pulling with equal forces on a center ring. And if they pull with equal forces, you recognize that that center ring isn't going to go to one side or the other. Well, that center ring could represent an electron. And if it's being pulled in the three directions evenly, it's not going to be pulled to any one side. It's going to be distributed in that molecule evenly, like this. No, not like that, like this. And so we find boron trifluoride is an example of a nonpolar molecule. Let's talk some about the macroscopic consequences of these molecules being nonpolar. Let's start with an easy molecule, nitrogen. We know nitrogen is nonpolar. We've got two atoms of the same sort. And so the electrons are going to be shared evenly between those two nitrogen atoms. They're nonpolar. We might ask ourselves, how would two nonpolar molecules feel about each other? Say these are two nitrogen molecules, and they're nonpolar. You don't have one side negative and one side positive. If they come by each other, they just might bounce off one another. There's not much of a force holding them together, and so they don't stick. As a consequence, we find they don't stick. Nitrogen is a gas at room temperature. You would have to bring the nitrogen down to a chilly minus 196 degrees Celsius in order for it to turn into a liquid form. Any temperature greater than that, there is enough thermal energy, that's not much thermal energy at all, but there is enough thermal energy to have it so that these come apart from one another. And nitrogen is a gas at room temperature. Let's contrast that with water, H2O. Here's the case for water. Oxygen has a greater polarity, a greater electronegativity, pulling power, than does the hydrogen. And so the electrons are pulled up towards the oxygen. And so the oxygen side ends up being slightly negative, while the hydrogen side of your molecule is slightly positive. We have a polar molecule. Here is a polar molecule. This side's slightly positive, and this side's slightly negative. How would another molecule of water feel about that? Well, here's another molecule of water. And this side's slightly negative, that side's slightly positive. Watch. They come together and they hold together, almost like magnets, but not magnets. There is an electric force of attraction between this negative side and that positive side, and so they stick together. And these are just two water molecules. We could take a bunch of water molecules all together like this and recognize they could orient themselves in such a fashion so that they are all lumped together and they may tumble over one another. And what phase do you have there? Why, you have the liquid phase, don't you? Now you understand how it is that water molecules stick together and how it is that water has a relatively high boiling point. It is because each water molecule is a polar molecule. Why is it polar? Well, because it's bent like this, and we can see how it is that the dipole here and the dipole there add up to one big overall dipole. So this side's slightly positive, that side's slightly negative, means two water molecules can stick together. Let's contrast that to a carbon dioxide. Carbon dioxide is a nonpolar molecule, as indicated by its boiling point, minus 79 degrees Celsius. Here are two carbon dioxide molecules. They're not very attracted to one another. They're each nonpolar. Water has a boiling point of plus 100 degrees Celsius. That's a big difference between these two molecules. Whereas it takes a little bit of energy to cause carbon dioxide to boil, it takes a lot of energy, 100 degrees, that corresponds to 100 degrees Celsius, to get the water to boil. Yeah, why? Because water is a sticky molecule. Water is a polar molecule. Got a question for you. Which is heavier, a molecule of water or a molecule of carbon dioxide? Which is a gas at room temperature? Which is a liquid at room temperature? These are the questions we're going to be able to answer as we now move on to Chapter 7. You have the basis for Chapter 7 as we talk about the polarities of molecules. Got that? Good chemistry to you.